Okay, so in the right side I've given basically how to plot, use these stem plots. Okay, so you need NumPy for making these arrays, and you need this matplotlib.py plot for plotting purpose. Okay, that library you need, right? So so first thing is that you define what is x. Okay, x-axis. So it's so in this purpose, in this case, it's linearly spaced between 0 and 2 pi. Okay, and there are 41 points starting from 0 to 2 pi. And then you define what is y. The y is what? This function which I am plotting is e raised to minus x. So y is np.exp raised exp of minus x. Okay, and so. Uh, so this plot.stem basically plots me the stem, gives me the stem plot, but it will not display it. So if you want to see the plot, then you need to explicitly say that to show me the plot. So the way it can be done is plt.show. So that will explicitly show me the plot. If I run this thing, so basically it plotted, right? Okay, basically it plotted this thing, and my x-axis is starting from 0 to 2 pi, it comes to about 6.28, and y-axis is at x equals 0, e raised to minus x is 1, so you get 1, and it progressively decreases. Okay, that's what the plot is showing. Okay, so this is one kind of plot. So, but many times what we want is like we want a continuous plot. Even though we have these discrete x and y values, we want a continuous plot. For example, why we want is like many times you can't represent in your computer a continuous step, right? You need infinite. You need to define infinite number of points. You can't do it. But what you can do is like if you're taking points which are sufficiently close by, then you can interpolate it, and you get you get an approximate plot which is very close to what you want, very close to the function, the continuous function which you want. So in those cases, you don't need this stem plot. It makes much more sense to have a continuous plot. So the way to make this continuous plot is by called as instead of plot, instead of stem function, you can use plot function. Okay, so if I use this by plot, okay, instead of by stem, plot stem, if you use plot, so it will give you a continuous. It will give me a continuous this thing. Okay, if I run this thing. So right now I'm getting a continuous plot. Earlier I was getting a discrete stem plot. Now I am getting a continuous plot. So what it did is like the values which it doesn't know the values. So you take two consecutive points and it join these two using straight line. But if the lines are very close by, you will not be able to see that piecewise linear curve. You will get you will see a smooth curve. So so that's what we are seeing here, right? Okay, so this is about plotting vectors. You can also plot images. Like you can also plot matrices. So if you want to plot matrices, you can't use this XY plots. You need to use something like an image, right? So the way you can image is or using what is called as IM show. Okay, you can use this instead of plot. You can use this IM show for this. Okay, so let me first make an 2D array, okay, to a matrix. So again I am just giving you some new functions using NumPy, so which are common, and this helps you in building your own intuition, and so you'll be able to see new functions. So I think it will be helpful. So once you start doing some project, something with these codes, it will be helpful if you know these small things. So there is one more in NumPy function which is called as IEYE. So basically it gives you a unique matrix. Okay, so np.I of 10, gives you a 10 by 10 matrix, a unique matrix. So what does that mean? That means the diagonal values are 1, all the off diagonal elements are 0. Okay, so I have constructed this a matrix as np.I of 10, then I can use im show function to basically plot this image, right? So it will be an image, right? It's a matrix. So with the diagonal values as 1, all other values are 0. Okay, I can use this plot.im show to plot this image. Okay, im show is for plotting images, image show. Okay, but again, you have to explicitly say that to show me the plot, otherwise it will not show you. Use this plot.show. Okay, so if you run this thing, so what you get is a color image, right? And so the way to interpret this thing is like yellow has higher values, and I don't know what is that other color that has 0 values. The yellow has 1 value. Okay, so ideally you need to have this color gradient also, which is it should be plotted here to make sense out of this. So there is an alternate way, is like to plot black and white, right? That we are familiar with. If it's white, it means higher values. If it's black, it's lower values, right? So we are much familiar with this thing. So we can have a black and white image. So the way to do it is like you have to use a alternative map actually. So you have to use this CM. Okay, it's a sub function. Okay, it's to basically CMax color map. So basically, it gives you which color map you need. Which is something like which gradient, which color you need. So it's a mapping of red means whether this what does this color represent, what should this color represent. So it's an you don't have to know much, but it's kind of mapping higher values to which color, lower values to which color. It's that mapping. So inside CMap there are many options. Okay, so what we do is like we specify what kind of color map we need. So if you specify that we need gray means white, it will have only black and white colors and a combination of black and white that forms your gray. And if it's white means values maximum, and if it's 0 means you will get black, right? And any value in between 0 and 1, yeah, you'll get a gray value, gray color with the intensity changing according to the value. Okay, so you specify the CMap as gray color. Okay, if you do this thing, you will get a black and white image, and it should make you much more sense, right? Yeah. So you have diagonal values 0, 0, 1, 1, 2, 2, having white color representing value 1, and all the other values are 0. So this gives you much better interpretability, right? This is much better interpretation. Right? So uh, this is about plotting functions. Okay, you can plot vectors. You can plot matrix using as an image, and there are a lot of other things that you can do. You can have bar plots, pipe plots, a lot of other things. You can have multiple plots clubbed together. You can have more than one plot shown together. So these things, there are a lot of features inside Matplotlib. You can go through these things. So some of these things will be helpful for you. But I am not going to cover all these things. So The aim is to give you basic understanding so that you can learn for yourself the solution as you learn. So next topic which we will be covering here is about solving system of linear equations using Python. Okay, so what is system of linear equations? So we have set of equations. You can go back to your linear algebra class. So you have a set of equations. Okay, and you want to see what is the x, y, z value, which will solve you, which will basically solve that set of equations. Okay, and here we are looking at the most basic case. Okay, where you have n set of equations and you have n set of unknowns. Okay, so I have given you an example. So x minus 2y plus 3 is equal to 6, 2x plus y plus 6 is equal to 2, 4x plus 7y plus z equal to 1. Okay, so how do you go to your maths class? So the way to solve it is like, first thing is to write it as a matrix form. So in matrix form, ax equal to bu, right? Okay, and a is what? A is the coefficient matrix coming from all these three equations. Okay, what is the coefficient of x? That forms your first column. What is the coefficient of y? Forms your second column. Coefficient of z forms your third column. That is how you construct your A matrix. And your x is small. The A, capital X matrix is unknowns x, y, z. Okay, and your B matrix is what? 6, 2, 1. Okay, vector 6, 2, 1. So that's so once you get this A and B matrix, then you can find the solution, right? So the way first thing you should do is like you say so first thing is you should do is like you need numpy. Okay, you use numpy, and then you okay. So first thing is you define your matrix A. Okay, so A is, as I told, can construct this A. Okay, and next is you want to know how many number of unknowns are there. Okay, number of unknowns are related with number of columns you have in A, right? Right. If you, it's very straightforward, right, to see that, because what first column is formed by x, second column is formed by y, third column is formed by z. So it makes sense if you count number of columns of A, it will give you number of unknowns, right? That's how you the way to find the how will you implement it? So small n represents number of unknowns. So there is this function called as a dot shape. So that will basically give you how many rows you have, how many columns you have. Okay, and the second argument of a dot shape should be number of columns, right? So and the second argument you select the indexing starts from 0 in Python, right? So if you want second term, you should give 1. So that's how you get a dot shape of 1. So this will basically give you number of columns in A, and that is same as the number of unknowns you have, right? So now you need to also construct your B matrix, right? B matrix is what? B matrix is formed from the right hand side, RHS. Okay. Now, once you have constructed this thing, so if you remember your linear algebra class, there are some set of things which you should do before you can find the solution. First thing is that whether you have to check whether you have a solution. Okay, and second thing to check is that is the solution unique, or you have infinite number of solutions. Okay, and only if you have unique solution, then only there it makes sense to finding the solution. If you are having infinite number of solutions, that's a different thing, right? You say that equation lies in this thing, something like that. So the problem which we are addressing here using Python, what we will be doing is like we'll be finding the solution only if you have unique solution. Even if you have multiple number of solutions, we will not we will not be finding the solution. Okay, so if you remember your linear algebra class, So how will you check if you are having no solution? Is like first you check what is the rank of A, then you check what is the rank of this matrix found by appending your A matrix with the B matrix towards your right. Okay, you construct this AB matrix and you see whether the AB matrix has the rank same as the rank of A. These two ranks doesn't match, then there is no solution. Okay, but if these two ranks match, but it's less than your number of unknowns, then you have infinite number of solutions. Only if you have this rank of A equal to rank of AB equal to the number of unknowns, then only you can find this unique solution, right? So the aim is to check these two things: whether rank of A is same as the rank of AB, and is that same as the number of unknowns. Okay. So again, MATLAB, this NumPy has this this function called as the matrix rank, okay, which lies inside this linear algebra subfunction of NumPy. Okay, so that we can use to see the rank. Okay, so I'm directly using this np numpy dot linear algebra is a sum function inside numpy, and inside that subfunction you have this function matrix rank. So that basically gives you the rank of the matrix. Okay, so basically you print what is the rank. Okay, okay. Then so that should basically print you the rank of A. I run this function. It says the rank is 3. Also, your number of unknowns is 3. So if rank of AB is also 3, then it makes sense to find the unique solution, right? So how will you check whether the AB has rank? So then you have to construct this matrix AB, right? You have a matrix A, you have a matrix B, which is two different. Then now what you have to do, you have to concatenate the matrix B towards the right of matrix A. You have to build that matrix. So that again you can use NumPy. There is another package, so called what is called as concatenate. Basically, it will concatenate A with B. But the thing is that you can concatenate towards the left or from the bottom. So there are many options, right? So Python for Python should also specify from which axis you have to concatenate. So so AB, so this concatenate matrix can be made using this NumPy command called as concatenate. Okay, so then you give the first matrix, commas B, the second matrix, so it will concatenate these two matrices. But you also need to give what is called as this axis. So if you give axis as 1, it will concatenate toward the right. If you give axis as 0, it will concatenate at the bottom. Okay, bottom of B will be concatenated at the bottom of A. Okay. So if we need A, B, we will concatenate at the right hand side of A. So then we specify that axis should be 1. Okay. Then we basically use this, and if you want, you can see for yourself AB is what it's claiming. Okay, what I have claimed. Does this actually makes? So you can see your AB matrix created is something. So this forms your A matrix. This is what your B matrix was. So it has properly made that. Okay, so B matrix. Okay, now what is remaining is check whether rank matches. Okay, so for that purpose, I'll just you again using this linear algebra dot matrix rank that function to basically see the rank. Okay, don't need this. Now if I run it, okay, so the rank of A is 3, rank of AB matrix is also 3. Also, the number of unknowns is 3. So this function luckily has a unique solution. So now we can go and find what is the solution. So the way to do is, so you should be knowing if Ax equal to B, the way you can solve A is a square matrix is A inverse B is your solution, right? So so you have to do this inverse operation, okay, matrix inverse. So the way to do this matrix inverse is using this numpy. There is a function called as np dot linear inverse of. So there is this function called uh, inv, which will compute the inverse of this matrix, okay. And this is inside this subfunction linear algebra subfunction, okay. Also, you need to multiply inverse of this matrix A inverse with B, right? So you need to have these two numpy matrices. You need to multiply these two things. So for multiplying two matrices, you have this numpy, another function, numpy dot math MIT so that multiplies these two functions. So this is why I told in the beginning that NumPy is a very good package. It has a lot of these matrix operations. So that's why many people prefer using these things. So the solution will be what? Solution will be what? It should be x here. Okay, x is what? Uh, uh, X is what? X is you multiply inverse of matrix A with B. So the way you do is like this. What is shown here? So if you do this thing and see the solution, if you do this thing, you get this solution. So we'll comment out all these things. Don't need these things. We have already checked. So basically, you get this solution 3.9096, y is minus 2, z is minus 0.6363, something like that. So you got this solution. So how will you check whether the solution answer we got is correct? Just take any equation, put the value of x, y, z to that equation, see whether left hand side is same as your right hand side. Right? So that sanity check also to take. I just took the first equation. First equation. So what is the left hand side is x minus 2y plus 3z. So now since we have this x minus 2y, x is now we have x minus 2y. So you have the value of small x, small y, small z. So this capital X matrix has all these three things. Right hand side is 6, right? So your left LHS should also be 6, right? Just see if it's coming that way. So if you're checking whether routing solution is correct, RHS the equation is 1 is 6, LHS is 6. Okay, so left hand side meets with the right hand side, so we got the correct solution. So this is how we solve a system of linear equations. Okay, so we use the concept of rank, we use the concept of making two matrices. Okay, so one thing which I not okay, so this one we can do, and one thing which I have forgot to include in the codes is you can find. So we are done with uh, solving system of linear equations. So one thing which I forgot to include is finding the eigenvalues of the square matrix. So you have this function inside linear algebra, to some function which you can use to find the eigenvalue of a matrix. So you just Google it. It's very straightforward. So I think you know what is eigenvalue decomposition. So you have a matrix, square matrix, which has an eigenvalue, which has under certain conditions, okay, you can write it as product of three matrices, okay, and the first and last matrix, first matrix is the inverse of the last matrix, and the first matrix has all the eigenvectors stacked together, and the second matrix is a diagonal matrix, the diagonal entries being eigenvalues, and the last matrix, the third matrix, is the inverse of first matrix. So like that you can have this decomposition. So I forgot to include that in that thing in your codes, so you can go and see online. So it's very straightforward. So what I have included is what is called as singular value decomposition. This singular value decomposition is I am not sure whether you have studied this singular value decomposition in your linear algebra course, but the way the what singular value decomposition is giving the uh, just so basically this singular value decomposition, what it basically gives you is like you take a matrix, any matrix, okay, it need not be square, you have an m by n matrix, you can do this suppose that matrix is A, okay. So that's what I have written here. Suppose you have a matrix A which has a dimension of m by n. Okay, it can be decomposed into a product of three matrices. Okay, so A can be written as UDV. Okay, and U is what? U is an m by D matrix. Okay, D is a dimension which is which depends upon what is your m and n. Okay, so U is what? U is an m by D matrix. Okay, okay, which contains what is called as your left singular vectors. So don't I am not going into details of what is this left singular vector, singular values. Okay, just know that these things exist. So if you are interested, you can see you take any standard textbooks on linear algebra, you will see what is this 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 what is this singular value decomposition, what does it do, and why is it that much, why is that very significant. Okay, uh, then you have the second matrix D, which is a diagonal matrix which has a dimension of d by d, and these diagonal values are your you have these diagonal values which we call it as what is called as the singular values of A. Okay, and then you have another matrix V which has a dimension of d by m. Okay, that has what is called as right singular vectors. Okay, so you can given any matrix A, you can have this decomposition equal to UDV. Okay, and so how you compute this UDV are beyond the scope of this course, okay? But you can always refer to standard textbooks. You will be able to see how you can do these things. But so what I will be showing now is like I show that you have a MATLAB, sorry, Python function inside NumPy, inside linear algebra sub function, sub library. You have this function called as SVD, so which basically computes you the singular value decomposition matrices UDV for given any matrix A. Okay, so the way, so I'll show you with an example. So I'm constructing a random matrix of dimension 200 by 100. Okay. So I discussed earlier how to construct this. You use the np.rand random.rand. So you have this rand. So it will create you a random matrix. So I've kept z0 so that I can repeat the result and show you that I can reproduce the result. So that's why I kept the seed, fixed the seed. Okay. So you have this function uh, inside np linear numpy inside linear's sub library. You have this function svd. So this you can use to get the decomposed udvs. Okay. And if you print, you can also print and see what is the shape of these things. So you can see my original matrix was of the order 200 by 100. Okay. And so we have your U matrix, first matrix, which is of the order 200 by 100. The second matrix, D, should be 100 by 100, but currently, so it's showing 100, so it has not become a matrix form. We'll see why is it this way. And you have this V matrix, which is 100 by 100. Okay, so if you plot what is D, print and see what is D, what is inside D. So D should ideally be a diagonal matrix, right? That's what I've told, but we are not getting that. It seems like it's not a diagonal matrix. We'll see what is. So is a set of values. So these you have 100 values. Okay, these 100 are one singular values of this matrix. Okay, and if you see, it's arranged in the descending order. You have 70.28. It's greater than 6.88 and 68. So it's arranged in the descending order. But it's just given you these singular values. It has not made you that matrix. So you need to make that diagonal matrix, right? So that also has another there is another function to make this diagonal matrix. Okay, so you can use np.diag. So that's this function to make diagonal matrix. np.diag will make you this diagonal matrix. So now if you see, the last is this 100 matrix, the from this single values. Is np.diag. So it makes here you give the vector of these values. In this case, it's this simple decomposition values. You give this as input. So that was a vector. So the result is an to be a diagonal matrix. Okay, so we can see whether we have what we are saying, what I am claiming is correct. So right. So if indeed U into D into V is A, then I can use this UDV to reconstruct A, right? So I first multiply U with D, then I multiply with V. That should give me A, right? So I can use that concept. So I use two matrix multiplication operation here, and I have reconstructed this matrix. Okay, so this reconstruct full. Okay, that should ideally give me. So this is U into D into V. That's what I have done here. So this should ideally should give me A back, right? So if that's the case, then if I do A minus A reconstruct full, okay, that should be a zero matrix, right? And if I see the error, which is something like I find out. I first find A minus A reconstruct. Okay, that should be a zero matrix, and I square the terms, each terms, and add it. That should give me a zero. So error should be zero, right? If A is completely equal to A square, means A reconstruct full is completely equal to A, right? So that's what I will do. So the thing which I told you, right? I do this difference, then I get a zero matrix. Okay, that is the, and I'll take each element, square the error, and add it. Right. So this operation is what is called as Frobenius norm. Okay, and again NumPy has this function norm to find this error. So if I do this error analysis, and if I see what is this error, ideally I should get zero, right? Yeah. Okay. So let's see what. So I'm getting an error 3.2529 into 10 to the power minus 30. So I'm the error for full matrix is not zero, it's to zero. So this small difference comes because of this machine precision issues of the here pattern, like so this truncate, some kind of truncation errors happen. That's why we are getting a very small value. Ideally, it should be 0. Now, so you can safely believe that it's very close to 0. But having this singular value decomposition is that in many cases, these singular values, the magnitude of these singular values, if it's higher, that means that vector that has more if you when you are reconstructing, that gives you more contributions. Okay. So their singular values are very close to 0. That means those terms you can neglect. Even if you neglect those terms, you can still get back your original matrix A. Okay, you can get very close to your original matrix A. So that's what we will be trying to do now. Okay. So what I'll do is I'll try. So here I've used the entire UV, W, sorry, UD and V entire matrix to reconstruct. Now what I'll do, I'll take only first few significant singular values and try to reconstruct. Okay. So the significance is given by the magnitude values of your singular values. Okay. But luckily for our case, this D matrix is ordered is descending order, is in descending order. So the first singular value has the largest value, and as you move along, it becomes smaller and smaller. Right. So it makes sense to take first n singular values and find out what is the corresponding left singular set of left singular values, set of right singular values, so right singular vectors, left singular vectors, and use that to try to reconstruct A. Right. So that's what I'm doing in the last part. Okay. So I'm since my matrix is 200 by 100, I'll have 100 singular values. Okay. N is what? N is the number of singular values which I want to take. So I just give 50. That means I'll take first 50 singular values and I'll try to reconstruct. Okay, the way to reconstruct this is using this matrix operation, U into D into V. But now I will not take all the U's and all the V's. Right? I'll take only the U's. I'll take only the first n vectors. Okay, of U. So the way to represent is so n columns of U, right? First n columns of U. So the way to represent U is that you take all the elements in first column, all the elements in second column, up to all the elements in the nth column, right? So, this column represents that all the elements along the column. Okay, take that thing. Then you select from 0. 0 means your first column up to n. N means your n minus. So right to n means n is not ordered, right? So 0 to n minus. So it will basically this 0 to n will basically select the first n columns of U. Okay. Then the D matrix has what has 100 is 100 by 100, but we'll take only the first n values. Okay. So from 0 to n number of rows, 0 to n number of columns. You basically take that small matrix out of your big D matrix. Okay. Then you multiply from V, you will select only the first n rows. Okay, so you write in the paper and see why we are taking columns of U and rows of V. Then only the matrix multiplication becomes possible. So you write it in the paper and see why is this happening. So if you do this operation, I'll get basically using first 50 singular values, I'll be able to partially reconstruct my matrix A, right? And we can vary this n. We can increase and see what happens, decrease and see what happens. Intuitively, it makes sense that as you increase n, it becomes much and much closer to your A, right? As you decrease your n, it should be much and much far away from n. And so the how you quantify this is using this reconstruction error, which I discussed earlier. Okay, so you have this Frobenius norm. So just we'll just plot this thing and see. We'll just print out and see what is the error we are getting. So here we are taking the entire matrix and seeing the error. This is almost, this is ideally should be 0. It's very close to 0. And see with first 50 eigenvalue, singular values, what the value, what is the what is let's see. So you see, getting a value 19.07. Ideally, it should be 0, but you are getting something like 19.0. So we can redo this thing and see what is this, what is that we are getting. So it should be less than 19, right? We are increased the number of single values which you are, and we can see here that it becomes from 19 increased 10. Okay, so ideal value is 0, but we are able to reduce the error. So as you increase your number of singular values you take, you will get better, you get better approximation, right? So uh, 90 and 95, for example, let's see what happens. So it should be less than 8. Okay, so it become almost very close to means it becomes very less. What happens if I put only 1? Only the major eigenvalue if I take is the from 40 as increased to 95, it came to about 3. So it changes. The error keeps on decreasing as you increase how many number of single values you are taking. So I'll stop here. So in the assignment, I'll ask you one of the questions which I is see for all the ranks possible. Take this 100, 200 by 100 matrix system. You see for all the ranks possible. You start from rank equal to, sorry, taking only single. Then you keep on doing it up to the 100 and see how the error behaves. Okay. So that will be one of your assignments. Okay, so I'll stop here. So I'll share you these Python scripts and the video. Okay, you can go through these things and try to attempt. You should be. So if you have understood the scripts, if you understood the lecture, it will be very straightforward to do the assignments. Okay, so I'm looking forward to see your answers. Okay, so I'll upload the question paper and these things today's. Okay, thank you.